before you can read it. But the output says 6 volts. So this is a step down transformer. In fact, it's stepping down from 120 down to 6. That's a factor of 20. So the voltage in the output, 6 volts, is 20 times less than the voltage on the input, or the primary, which is 120 volts. So it's a step down by a factor of 20. You're going from 120 down to 6. It's 20 times smaller from the primary to the secondary. So, how many turns are in the secondary? Well, divide 1,000 by 20, and you would get 50. So on this one, if there are 1,000 turns on the primary at 120 volts, then there's 50 turns on the secondary that gives us an output of 6 volts. It steps down 20 times, only 5% of the voltage in turns on the secondary compared to the primary. So, now there's another thing that we have to consider, is that voltage and current, they're inversely proportional. So let's see, do you remember Ohm's law? It says V equals I times R. Well, if R stays constant, then what happens is V and I guess probably the better way to tell you is using the power law. P is equal to IV. Because in this case, we have to use the law of conservation of energy. That says the energy coming into the transformer can't be greater than the energy leaving the transformer. The energy of the primary can't be greater than the energy of the secondary. And that means that the power, which is the rate at which energy is used, the power of the primary can't be greater than the power of the secondary. But in fact, in a very efficient transformer, the power on the primary is going to be equal to the power on the secondary. So if the power is the same on either side, the power can't change. That means I times V can't change. So if it's a step up transformer, V is getting greater, it means that the current has to step down by the same factor. Or if it's a step down transformer, which means V is getting less, for the power to remain the same, then I has to increase by the same factor. So I'm going to add one bit to this equation. The inverse happens to the current. So if the ratio of the number of turns in the primary to the secondary is equal to the ratio of the voltage on the primary to the voltage on the secondary, then that's equal to the ratio of the current on the secondary to the current on the primary. It's the opposite. So the opposite things happen. So in this one, for example, I have a voltage of 30 volts. In other words, the voltage has become 4 times less. Well, what I know is that the current has become 4 times greater. So let's take a look at that and sort of see what's going on. So let's take a look. What is our light bulb? Do you remember what our light bulb voltage was? I think our light bulb resistance. Let's say the resistance of that light bulb, I think I remember it being 6 ohms when we used a light bulb in our last example. So let's just take a look here. I've got this step down transformer, and I've calculated this. I started with 120 volts. It was number of turns was 250 in the secondary, 1,000 in the primary, so this was a step-down transformer, ended up with 30 volts in the secondary. So what was the current in the secondary? Well, I can calculate that because I know the load is 6 ohms. So I'm going to say the current in the secondary is equal to 30 volts, which is the voltage of the secondary, divided by 6 ohms, which is the light bulb, and that gives me 5 amps. So 5 amps is flowing through there. Okay, so here's the question then. If 5 amps is flowing through the secondary, how much current is on the primary? Well, we found out that because of these turns ratio, that the voltage was 4 times less, 120 to 30. That means the current is 4 times more. So, to find the current on the primary, here's what we'll do. We can arrange this to solve for that using the number of turns or the voltage. I'm going to say the current on the primary is equal to, and I can do it like this if I want. Let's just use the voltages since those are known. So I'm going to say the current on the primary is equal to the current on the secondary multiplied by the voltage on the secondary divided by the voltage on the primary. So I rearrange this portion to solve for the current on the primary, and I get this. And so that's equal to current on the secondary is 5 amps. Voltage on the secondary is 30 volts. Voltage on the primary is 120 volts. And that's equal to 5 times 1 over 4. It reduces to 1/4. So 5/4, which is equal to 1.25 amps. So notice that for voltage, the primary voltage is 4 times less than 120. But for the current, the secondary voltage is 4 times less, 30 volts compared to 120. But the primary, the secondary current is 5 times greater. So secondary voltage is 5 times less. Secondary voltage is 5 times less. 4 times less. Oh wow. Secondary voltage is 4 times less. Secondary current is 4 times greater. So 5 is 4 times greater than 1.25, which is the current on the primary. Alright, so let's kind of check that real quick. Just to make sure that what we have is working out. Okay, so I said that the power has to be equal the whole time. So let's just do a quick check. And this is the problem I'm working out is very similar to number 3 of the homework, by the way. So I'm going to say, what is the power on the primary? I'm sorry, not number 3 on the homework. This is very similar to number 8 on the homework. A little bit different. So the power on the primary is equal to the current on the primary times the voltage on the primary. And that is equal to, primary current is 1.25 amps. The primary voltage, remember, was 120 volts. So it's 120 volts, 1.25 amps on this loop. And I multiply those together, and let me calculate what that is. .25 times 120. That's equal to 150 watts. Remember that the power is measured in watts. We learned that last semester. What about the power on the secondary? Well, that is equal to the current on the secondary multiplied by the voltage on the secondary. So the current on the secondary is 5 amps. We're going to multiply that by the voltage on the secondary, which is 30 volts. And that gives us a power on the secondary, 5 times 30 is 150 watts. That's just a quick verification to show you that even though the voltage is 4 times less on the secondary, but the current is 4 times more on the secondary, the ratio, the product of current and voltage is the same for the primary as it is for the secondary, due to the conservation of energy. Alright, so I mentioned number 3. Let's talk about another component. That's the inductor. Makes transformers possible. If it weren't for transformers, there's so much that we could not do electrically. There would be no AC induction motors, like electric drill press. You plug into the wall and you drill a hole in something. That's not possible without transformers and induction. Another thing that's not possible: long-range transmission of electricity. The big power lines that go overhead. Why is that made possible by transformers? Well, when current flows through wires, those wires get hot. So the more current, the hotter it gets. And that heat dissipates, it's a loss of energy. When we create energy at a power plant, it's pretty low voltage. And the current is huge. And we try to send that through wires and it dissipates into space and the wires get really hot. So we can't send it for long distances because it just gets used up in the air. So we use a transformer to jack the voltage up to hundreds of thousands of volts, take the current down to tiny, tiny little milliamps, and now we can run it along those wires, and the wires don't get hot because the current